So the plan for today is to just try to use the Laplace transform that we learned to solve for any circuit. We learned that if we have a circuit in time domain, regardless of the type of source that we have, we can go from time domain to the S domain and solve the circuit in S domain. And since there is a unique relationship between S domain and time domain, I can always go back to time domain and have the solution. The only catch here was the elements that we had did not quite translate to like S domain. If we had like a resistor, it directly translated to S domain. We didn't have like any issue. It basically matched our intuition from the frequency domain. But if we had a capacitor or an inductor, it did not quite translate to the S domain. And our translation to like the S domain was that value followed by some source, where the value of the source was controlled by initial conditions of the capacitor or the inductor. And if you recall, if we have an inductor, we know current through the inductor is continuous. And we know the voltage source that came right after the S domain version of the inductor was related to this initial condition. And the same thing for the capacitor, right? So to quickly like refresh your memory, let me just write down like all those elements and then do a few examples. Okay. So recap. Let's just say I have these elements. And this is VT-IT relationship. And assuming the Laplace transform of Vt is V of S, Laplace transform of I of t is I of S, this is the VS-IS relationship. So let's start by looking at a resistor. We know if we have a resistor with value R, current through IT, voltage across Vt, we know Vt equals R times IT. And the good news was, if I have like this resistor, I can just grab it and just put it in the S domain with no change. So I have this resistor in S domain, the value R, nothing changes. Current through it becomes I of S, voltage across it becomes V of S, and I know V of S is R times I of S. So life is pretty good. Now we have the inductor. Which requires us a little bit of like more care. Let's just say I have an inductor with value L, current through IT, voltage across Vt. I know Vt equals L dit dt. But I know as soon as I go from time domain to the S domain, to my Laplace domain, this L becomes these two elements all together. So I have this equivalent inductor with value SL, followed by a voltage source with polarity negative positive, with the value L times I. And if I consider current through it I of S, I know if I'm asked to find this Vt over here, this translates the voltage across these two things together and not just this S. So this is V of S. Right? And we also talk about like the source transformation. We said we can use like source transformation and convert this voltage source to a current source. So we can use source transformation and redraw this equivalent circuit. The value of resistance would not change. This voltage source becomes a current source in parallel. And the value of this current source is I at 0 divided by this. Right? Remember, this I evaluated at 0 is the initial condition of this inductor in time, which we do know is a continuous variable. Right? And the last case, the last element that we have is a capacitor. So if I have a capacitor with value C, let's just say current through it is IT, voltage across it is VT. I know IT is CdVT. And the whole thing over here in time domain becomes this 1 over SC followed by a voltage source with value V0 divided by S. If I say current through it as I of S, voltage across both of these elements together is the same as this VT. So this is Vs. And obviously we can use like the source transformation and get the equivalent version of it, which is 1 over SC, followed by a current source. This time, this current source is C V naught. Right? Remember, voltage across a capacitor is a continuous variable. Therefore, when I'm computing this V at time 0, I know this V at time 0 is the same as V at time 0 plus, is the exact same as V at time 0 negative. Right? So I can simply compute it. Right? The whole idea here is that I can replace any of these elements by their equivalent in the S domain. And as soon as I basically know how I convert it to the S domain version of it, the rest of it is like a resistive circuit. I can treat all these elements as a resistor and use my favorite method to solve for whatever the question's asking. Okay? Let me quickly do an example. Let's just say I am given this circuit. I have a 12 volts source. I have a switch that becomes open at time 0. I have a 6 ohms resistance followed by a 12 ohms resistance and a 2 Henry inductor. The question is, what is this I of t for times gradients? Right? Before we solve this, I want you to pay attention to something. In this circuit, I don't have any UT. I don't have any step function. But if you recall when we're talking about like step function, I said a step function acts like a switch. And since I have like this switch over here, that is basically telling me the source that I have here is kind of like a step function. It's not exactly U of t because this switch is closed when t is negative and it's open when t is positive. So it's basically U of negative t rather than U of t. But again, it is still a step function, right? Regardless of that, I need to find I of t, which is current through that 12 ohms resistance, for times greater than 0, right? What does my circuit look like for time greater than 0? So for time greater than 0, I know the switch is open. If the switch is open, what it means is that this portion of the circuit is completely gone, right? So this is basically the circuit I have. So I'm going to redraw it. I have this 6 ohms. I have this 12 ohms. And I have this 2 Henry inductor. And the question is, what is this IT? Right? Obviously, I can write the differential equation. I can solve for it. I can find exactly like what IT is. And I can do that. An alternative way of approaching this problem is to use Laplace transform. But remember, if I want to just do Laplace transform, I have to find the S domain version of every single element that I have. For the resistor, I don't have an issue. Whatever value it has, it's the same in the S domain. It's just this inductor that has some source attached to it. So remember, reminder, if I have inductor with value L in time domain, if I go to S domain, this inductor becomes S times L, followed by a source with value L, IL at time 0 plus. Right? That is basically our equation. But what is this IL at time 0 plus? We know IL at time 0 plus is continuous. Therefore, it's exactly the same as IL at time 0 negative. Right? We know IL at time 0 plus is exactly the same as IL at time 0 negative. Right? But what does my circuit look like at time 0 negative? I got the whole thing. The switch is closed. I got the whole thing. So I have this 12 volts. The switch is closed. I have this 6. I have this 12. What happens to my inductor? Right at time 0 negative, I'm in a steady state condition, right? What happens to an inductor when we're in the steady state condition? It's a short circuit. So I have this shorted out. And obviously this is IL at time 0 negative. What is IL at time 0 negative? Well, I have these two elements in parallel, and it's in parallel with this 12 as well. Therefore, voltage across this 6 is 12. Voltage across this 12 is also 12. So what is IL at time 0 negative then? It is 12 volts divided by 12 ohms, which is 1 amp. As soon as I know IL at time 0 negative, I know that's the same as IL at time 0 positive. Therefore, IL at time 0 positive is 1 amps. Right? No, I'm done. I know exactly how this 2 Henry inductor is in S domain. Right? So I know this 2 Henry in S domain. I have to replace it by SL, which is 2 times S, followed by L times IL at time 0 plus, which is 2 times 1. So it is 2. Right? Now I know exactly what my circuit looks like in S domain. So redraw this circuit in S domain. What do we have? We have this 6 ohms. It remains the same. I have this 12 ohms. That remains the same. This inductor becomes this 2S followed by this 2. And the question is, what is this I of S? Right? Is that clear how I drew this circuit in S domain? I replaced every element by its S equation. Right now, I know exactly how to analyze this. I treat every single element I have as a resistor. So I'm going to write a KVL here. I'm going to write a KVL. Let's start here. I have 6 times I of S plus 12 times I of S plus 2S times I of S minus 2. I close the loop. That must be 0. Right? So let me factor out this I of s. I have I of s. I have 6 plus 12, so it's 18, plus 2s equals 2. Therefore, I of s is 2 divided by 18 plus 2s, which is 1 over s plus 9. Right? As soon as I know what IS is in S domain, I can use the table to find I of t. Therefore, use the Laplace inverse and compute I of t to be e to the power of minus 90 ut. Right? Keep that in mind, like this ut that I have over here takes care of like that time greater than 0. Right? Because what it says is that like for all times greater than 0, my current is e to the power of 9 times t. Right? So that's it. Does that make sense how we're doing this? The whole idea here is that I have to find the equivalent of every single element that I have and redraw the circuit. Right? Let's do a few more examples and see how we can actually do this. Example. Let's just say I am given this circuit, 4 times ut, 3 ohms resistance, followed by 1 Henry inductor, plus or minus 12 times ut, 1 farad capacitor, followed by a 2 ohms resistance. And the question is, what is voltage across this 2 ohms resistance? Right? Before we solve this, what is the order of the circuit? It's 2, right? I have 2 storage elements. I have a capacitor, I have an inductor. So the order of the circuit is 2. Right? So I know I can write down the differential equation and solve the second order differential equation. Right? But let's just do the alternative way, which is the easier way, under the Laplace transform. Right? How do we do the Laplace transform? We're going to replace every element by the S domain version of that element. But to be able to write down the S domain version of this inductor and this capacitor, what do I need? I need their initial conditions. Right? So to be able to draw the S domain circuit, we need to know IL at time 0 plus and VC at time 0 plus. Why? Remember, if I have this inductor with value L in S domain, this is SL followed by a voltage source with value L times IL at time 0 plus, which I do know this is the same as L times IL at time 0 negative. Right? And this is because of the continuity condition that we have for the current through inductor. Right? And if I have a capacitor with value C, if I go to S domain, I replace it by 1 over SC, followed by a voltage source with value VC at time 0 plus over S, which again, we know voltage across the capacitor is a continuous variable. Therefore, this is VC at time 0 negative over S. Right? Regardless, we got to know VC at time 0 plus, IL at time 0 plus. Right? To be able to find these two, we need to look at a circuit at time 0 negative. So for all times less than 0, what does my circuit look like? Well, look at the source. I have 4 times ut. For time negative, ut is 0. What is a current source with the value 0? It's an open circuit, right? So I have this open circuit. I have this 3 ohms. I have this 1 Henry. How about this 12 times ut for time negative? What is a voltage source with value 0? It's a short circuit, it's just a wire. So I have this wire. And then I have this 1 farad capacitor followed by 2 ohms. Yes.
So when we see UT, we just always assume it's 0 at times less than 0, 1 at times greater than 0.
Yes, that's the
unless
definition.
stated otherwise.
No, that's the definition.
Always?
It's always
Okay.
this. Yes. UT is always 1 for times greater than or equal to 0. It is 0 for time less than 0. So this is my circuit for all times less than 0. What happens to circuit at time exactly equal 0 negative? So what happens if time is 0 negative? We're in a steady state condition. What happens to an inductor in a steady state condition? It's a short circuit. What happens to this capacitor then? It's an open circuit. So we're in a steady state condition. Therefore, my circuit looks like this. I have this 3 ohms. This becomes short. This is IL at time 0 negative. This becomes open. So this is VC at time 0 negative. And this is U. What is IL at time 0 negative? Well, just write a KVL in one of these loops. What does it tell me? It tells me IL at time 0 negative is 0. I immediately know IL at time 0 plus must be also 0. Right? How about VC at time 0 negative? Well, again, it's sufficient to write a KVL in this loop, which I can see it's a 0. Okay? Which I immediately know VC at time 0 plus must be 0. What does this tell me? It tells me if I go from this L in time domain to the S domain version of it, there is no voltage source because IL is 0. Same thing over here. If I have this C and I go to the S domain version of it, there is no voltage source. Therefore, this term is gone. Right? So let me quickly redraw the circuit in S domain. So redraw the circuit in S domain. What happens to my source? Well, I got no issues with the source. That's 4 times UT. I can look at my table. I know that's 4 over S. I have a resistor. The value of a resistor does not change. I have this inductor, which I know I have to replace it by the equivalent and a source, but the source is 0. So it is just SL. So I have this S. This voltage source becomes 12 over S. This capacitor must be replaced by 1 over SC followed by a voltage source, which I know it's 0. So it's just 1 over S. And then I have this 2 ohms resistor. And the question is, what is this V out of this? You with me so far? This is my circuit. No, I can't use my favorite method. Let's do nodal analysis for now. Okay? OA, nodal analysis. So let me quickly redraw the circuit. I have 4 over S, 3 SL, which is just S, 12 over S, 1 over S, and 2. I need to do nodal analysis. How do we do nodal analysis? Just have a quick review. How do we do nodal analysis? The first step is to choose a reference. Well, I choose the bottom node as the reference. What is the next step? To name all the nodes that we have, right? Do you agree this one up here is one node? Right? How about this one in the middle? Do you agree that's a new node? Let's just call it V2. Do you agree this one over here is also a node? But remember, like these two are already in series, so I can combine them to avoid naming a node. Right? So I can basically combine these two and write it as 2 plus 1 over S. Right? How about this one over here? The top left. Is that a new node? It is a new node. But remember, when we're writing the KCL, all we care is the current. Right? So I already know current through this branch. So I don't really need to name that node. Right? So I'm done. Right? What is the next step? Is to write down KCL for every single node down. Remember, when we're doing node analysis, voltage sources are either very easy or problematic. When are they very easy?
Between a node and the ground.
They're very easy when the voltage source is located between a node and the ground. When are they problematic? When they're between two nodes. What is our solution? We just go around it and define a supernode. In this case, that's the easy one, isn't it? So what is my V2 then? I know exactly what V2 is. V2 is 12 over S. So I know V2 is exactly 12 over S. All I have to do is to write a KCL at the top node. And then I'm done. Right? What does KCL tell me? It tells me whatever current that's going in must be the same as the current that's coming out. So I'm going to give whatever element, whatever branch that I don't have direction for a direction. So let's just say this is going out, this is going out. I cannot do anything with this branch because it's already going in. Right? No, I can write the KCL. What is the element to this branch? It is V1 minus 0 divided by 2 plus 1S, 1 over S. Right? What is current through here? It is V1 minus V2 divided by S. But I already know V2 is 12 over S, so I'm going to write it as V1 minus 12 over S divided by S. Right? I got no other current that's going out. So that equals to the current that's going in, which is this 4 over S. So this is KCL at V. Right? The rest is just like simplification. Let's just simplify it a little. So how do we do this? Well, I have V1 over 2S plus 1 divided by s plus v1 over s minus 12 over s divided by s. So it's minus 12 over s squared, but it's nothing to do with my unknown. So I can basically take it to the other side. So equals 4 over s plus 2 over s squared. Right? I can factor out this v1 over here. So I have v1 times s over 2s plus 1 plus 1 over s equals s squared 4s plus 2. Right? You with me? Yeah? Well, let's just simplify it a little more. I have v1 times s times 2s plus 1. I have s squared plus 2s plus 1 equals 4s plus 12 divided by s squared. What is this? Isn't it s plus 1 squared? It is. So this is s plus 1 squared. I'm going to cancel this s with this squared over here. So let's compute v1. v1 is 4s plus 12 divided by s times 2s plus 1 divided by s plus 1 squared. Right? But remember, that's not what I want. I want v out. How can I do this? Isn't it the voltage divider? I know voltage from here to here is V1. Right? Therefore, I know exactly what voltage across this 2 is. Do you agree with me? Or no? Does everybody see the voltage divider? So then V out is very simple. I know V out is 2 divided by 2 plus 1 over s times V1. Right? Let's simplify it a little bit. I have 2s divided by 2s plus 1 times V1, which is this term over here, 4s plus 12 divided by s times 2s plus 1 divided by s plus 1 squared. Right? This s and this s cancel. This 2s plus 1 and this 2s plus 1 cancel each other out. What I'm left with is V out of s equals 8s plus 24 divided by s plus 1 squared. Right? Remember, this is a voltage divider. Right? Now I know V out s. I can go to time domain. How? How do we go from s domain to time domain? How do we do inverse Laplace? We're going to do partial fraction decomposition. Right? So if I have V out of s, as 8s plus 24 divided by s plus 1 squared, I know I can write V out of s as some constant a1 divided by s plus 1 plus some other constant a2 divided by s plus 1 squared. Why? Because if I look at this, I have a pole at -1 that is repeated. So when I'm doing the partial fraction decomposition, I have to have all the elements up to the highest power. Now, the only thing I gotta do is to find A1 and A2. Well, we know A2 is like very simple. A2 is limit when S goes to the pole, -1, times S minus the pole, so it's S plus 1, times V out of S. S plus 1 squared times V out of S. This S plus 1 squared and this S plus 1 squared cancel each other out. So its limit S goes to -1 of 8S plus 24, which is 60. Right? How about A1? How do we do A1? To find A1, we have to take derivative of this one. Remember? That's basically like the case 2 that we had when we were doing the Laplace inverse. So that's limit S goes to -1 ds of S plus 1 squared V out of S. This S plus 1 squared and this S plus 1 squared cancel each other out. The whole thing left is 8S plus 24. If I take derivative with respect to S, what do I get? It's just an 8. Therefore, my V out of S is 8 divided by S plus 1 plus 16 over S plus 1 squared. Right? As soon as I have this, I know exactly like V out of T is. I'm gonna look at the table, and I know V out of T is 8 times e to the power of minus t ut plus 16 t e to the power of minus t ut. Right? You remember I started this problem by asking you like what order this circuit has? And we said 2. Given the solution that you're looking at, what type of solution do you think we got? Is it overdamped, critically damped, or underdamped? Well, look at it. I have exact same solution over here, but this time I have it multiplied by t. So what it tells me is that if I look at the poles are repeated. And as a matter of fact, I know exactly what the poles are. The poles are like -1 twice. So what kind of solution is this? It's a critically damped. Right? And this t over here kind of confirms that. If you remember when we were talking about like the differential equation method, when we're solving it, we said like if you have like 2 exact same solutions, we're gonna have to like multiply it by the t. And now this t is somewhat justified by looking at the Laplace version. Right? Let's try to do the exact same problem, but this time let's just do it like mesh analysis. So let's do mesh analysis. Again, remember my S domain circuit is still this. Nothing has changed. I have 4 over S. I have 3. I have S. 12 over S. I have 1 over S. And I have this 2. And the question is, what is this V? We said we want to do mesh analysis. How do we do mesh analysis? We're going to label the loops, right? So let's call this I1, call this I2. You remember when we were doing mesh analysis, current sources were either super easy or problematic. When are they easy? When they're in one loop. Right? When are they problematic? When it's shared between two loops. What was the solution for the shared current source? Again, we get around it and we define a super loop. Right? What is the case over here? This is the easy one. I know exactly what I1 is. What is I1? It's 4 over S. So I1 is 4 over S. What is the next step when we're doing mesh analysis? We're going to write KVL for every single loop. Let's just write a KVL for loop 2. So write KVL for loop 2. Let's start here. What do I have? I have 1 over S I2 plus 2 times I2 minus 12 over S. What is voltage across this S? It is S times, what is current through it? It's I2 minus I1, right? So it's I2 minus I1. But what is I1? It's 4 over S. This must be 0. Remember, this is I1. Right? The rest is just simplification. There is nothing to it. So if I simplify it, let's just factor out I2. First term over here, I have 1 over S. This term I have 2. This is a constant. I'll take it to the other side. This one I have S. That equals 12 over S. I have S times negative 4 over S. So it's negative 4. I'll take it to the other side. It's simple. Right? Again, I can simplify it a little more. I have I2 times common denominator here is S. I have 1 plus 2S plus S squared equals 12 plus 4S divided by S. Right? Again, remember this over here as S plus 1 squared. Right? This S and this S cancel each other out. I get I2 equal 12 plus 4S divided by S plus 1 squared. Right? Remember, I2 is not the one that I'm looking for. What am I looking for? I'm looking for voltage across that 2 ohms resistance. What is it? It's 2 times I2. Right? I know V out of S, it's 2 times I2 of S, which is 8S plus 24 divided by S plus 1 squared, which is exactly the same as this V out of S. Right? Obviously, I'm not going to find V out of T because it's exactly the same as like what we did. Right? But since V out of S is exactly the same, I know the solution V out of T must be the same. Right? So if we take the Laplace inverse, V out of T is 8 times e to the power of minus t ut plus 16 t e to the power of minus t. Right? So as soon as I have the circuit in the S domain, the rest is exactly the same as before. Right? Let's do superposition. What is the superposition? Anybody want to remind me what the superposition does?
Isolate each of the sources.
We basically need to find contribution of each source by keeping that specific source and eliminate the rest of them. Right? So again, remember my circuit does not change. My circuit is still this circuit. So I have this 4 over S. I have 3. I have S. This is 12 over S. I have 1 over S. And I have this 2. And the question is asking me, what does this be out of this? So let's find the contribution of, like, for example, current source. So contribution of current source. How do we do this? We're going to keep the current source and eliminate the voltage source. How do I eliminate the voltage source? It's going to be short circuit because the value of the voltage source is 0. A voltage source value 0 is a short circuit. So the circuit would look like this. That's 4 over S, 3 S. This becomes short circuit. This is 1 over S. This is 2. Let's just call this V out of S. 1 is the contribution of the first. Right? How do we do this? Let's do Newton cost. So I'm going to call this my ground. Call this V1. What is the KCL at V1? It is V1 divided by 2 plus 1S plus V1 divided by S equal 4 over S. Do you agree with me? I assume the currents are going up. Yeah? You with me or not? So let's simplify that a little bit. I have V1 over 2S plus 1 divided by S plus V1 over S equal 4 over S. I can factor out this V1. I have S divided by 2S plus 1 plus 1 over S equal 4 over S. I can simplify a little more. I get S times 2S plus 1. Right? So I have S squared plus 2S plus 1. That is 4 over S. Right? Again, remember this is S plus 1 squared. This S and this S cancel each other out. So V1 of S is 4 times 2S plus 1 divided by S plus 1 squared. Right? Again, this is not what I'm looking for. What I'm looking for is V out 1 of S, which is voltage across this 2. How do I do this? How do I do this? It's another voltage divider, right? Because I know V1 minus 0 is voltage across these 2. Therefore, I know voltage across this 2 ohms resistance. So V out 1 of S is 2 divided by 2 plus 1 over S times V1, which is 2S divided by 2S plus 1 times 4 times 2S plus 1 divided by S plus 1 squared. This and this cancel each other out. I got 2S divided by S plus 1 squared times 4, so it's 8S. Right? Yes? You with me? Fantastic. What is contribution of the second source? So what is contribution of voltage source? What is it? I'll keep that voltage source, get rid of the current source. How do I get rid of the current source? I open it. So my circuit looks like this. I have S, 12 over S. This 1 over S. And that's 2. And let's just call voltage across this V out 2. Right? Again, remember this portion is completely gone. Right? How do I find this V out 2? How do I do this? We know it. What is it? What is this circuit? It's another voltage divider. Therefore, V out 2 of S is 2 divided by 2 plus 1 over S plus S times 12 over S. Right? If you simplify it, given the fact that this is 8S divided by S plus 1 squared, and I know V out must be 8S plus 24 divided by S plus 1 squared, I'm saying this must be 24 over S plus 1 squared. You can simplify it. Right? What is V out S then? That is V out 1S plus V out 2S, which is 8S plus 24 divided by S plus 1 squared. Which again, I can find V out of T. V out of T is 8 times e to the power of minus t ut plus 16 times t e to the power of minus t ut. Right? Does that make sense how we're doing it? Again, whatever we had before still holds. If we know exactly how to do superposition in time domain, we can apply it in the S domain. Nothing changes. Let's try to do the same problem, but this time let's just do like Thevenin. Okay? See how we can apply Thevenin. So it's V Thevenin equivalent. Again, remember my circuit looks like this. S 12 over S, 1 over S, 2. Okay. How do we do Thevenin? What is the first step of doing Thevenin? Determine where the load is. Well, which one is the load? Well, I'm interested in this V out of S, therefore this is my load. If this is my load, what is the rest of the circuit? It's my black box. Right? To be able to find Thevenin equivalent, I need 2 things. What do I need? I need V open circuit, and I need R Thevenin. Right? How do I find R Thevenin? How do we do this? To find our Thevenin, we're going to look at our black box. Right? Do we have any dependent source in the black box? No. If not, our Thevenin is just equivalent resistance. What if there is a dependent source in there? How do we find our Thevenin? Well, this time I have to find V open circuit, I have to find I short circuit, and I have to divide them, and that's my RThevenin. Luckily, this is a very simple circuit. I don't have any dependent source. I could have, but I don't. Right? So what is my RThevenin? How do I find RThevenin? I have to zero out the sources. Right? So to zero out the source, if I have a current source, that becomes open. If I have a voltage source, that becomes short circuit. So let's find Z Thevenin. Right? I know if I have a current source, it becomes open. If I have a voltage source, it becomes short. And now I have a resistive circuit. I can find Z equivalent, which is Z Thevenin. What is my Z Thevenin? What is my Z Thevenin? Well, remember, like this is open. If this is open, this portion is completely gone. Then what is my Z Thevenin? Yeah, these two in series. So my Z Thevenin is S plus 1 over S. Right? What is the next step? To find the open circuit. How do we find the open circuit? We remove the load, leave those two terminals open, and we find voltage across them. Right? So the next step is to find the open circuit, which means this is my circuit. I have a 3. I have a S. This is 12 over S. This is 1 over S. And this is the open circuit. Right? What is the open circuit? I'm claiming it's like very, very simple. I don't even have to write down any sort of like equation, just Ohm's law. Why? Do you agree the open circuit is voltage across this S and this 12 over S? Right? Whatever voltage I have here, it jumps across this. Right? Do you agree if it's open circuit, there is no current flowing through this 1 over S? Therefore, this 4 over S, which is my current source, is going to entirely flow through this S. Right? Then do you agree I know voltage across this S? What is voltage across this S? What is it? Let's just call it like V1. What is V1? It's 4 over S times S. So it's 4. Therefore, what is V open circuit? It's V1 plus 12 over S, which is 4 plus 12 over S. Right? Now I have our Thevenin. I have the open circuit. I have the Thevenin circuit. I have the open circuit, which is 4 plus 12 over S. I have my Z Thevenin, which I just computed it as S plus 1 over S. So it's S plus 1 over S. And now I'm going to stick the load back in here. What is V out of S? We know it. What is it? It's another voltage divider. V out of S Again, it's a voltage divider. So it's 2 divided by 2 plus S plus 1 over S times 4 plus 12 over S. If you simplify it, B out of S is 8S plus 24 divided by S plus 1. Right? Which we can find B out. Yes.
I was thinking for like the top left side of the circuit, if it's 4 over S is the current and you have the 3 resistance, you could do 3 times 4 over S, but that doesn't work. Why is that? To find that nodal voltage.
What is it? Sorry.
Like if you use the left side of the circuit,
This one?
yeah, and
Okay.
you use 4 over S times 3 to give you the voltage.
That's voltage across this.
Okay, so it won't.
What is voltage across this?
Is it just we don't know?
You don't
That'd
know.
be
I mean, it's not 0.
The bottom should be 0, right?
No, voltage across this plus voltage across this is the same as voltage across these two.
So I only found the voltage across the resistor, and that's why it doesn't.
You have Ohm's law for a resistor. That's it. Right? That's why we have like issues with like current sources with writing KVL. Because we didn't know voltage across.
Ah.
Right? Let's do source transformation. We can do source transformation, right? Can we? Yeah, whatever we could do with the resistive circuit, we can do over here as well. So let's do source transformation. Source transformation. What is source transformation? Tell me. What does it tell me? It tells me if I have a voltage source, let's just say V of S, it's followed by some impedance, Z of S. I can redraw this as an equivalent circuit with a current source, I of S, with some impedance, which is exactly the same as this impedance. And if I call this A and B, this is still going to be A. Right? So assuming I'm given circuit on the left, I can compute the circuit on the right. This Z of S does not change. I know I of S is V of S divided by Z of S. So this is this direction. If I'm given the circuit on the right, I can find this V of S to be Z of S times I of S. The value of the impedance does not change. Right? You guys remember that? So how can I use this in this circuit? Remember my circuit in S domain as a still this circuit. I have 4 over S, 3 S, 12 over S, 1 over S, and 2, and this is V. Well, how can I apply this? Do you agree I can replace this portion of the circuit by something that looks like this? Right? So if I have S 12 over S, I can replace this by a circuit with, what is the impedance of the circuit? That's just exactly S, it doesn't change. Followed by a current source. What is the direction of the current source? It's upward, right? What is the value of this current source? It's 12 over S squared. Right? So if I do that and redraw the circuit, what does it look like? I have this 4 over S. I have 3. And then I have this 12 over S squared over here in parallel with this S. And then I have 1 over S over here and a 2 over here. Right? Let me call this current over here I. What is I? What is this I? I can write a KCL at this top node, right? I can write a KCL at this point and get I. Right? Can I? So what is I then? I is 4 over S plus 12 over S squared. Yes or no? Do you agree I can combine these two? I can, right? That's 12, well, 2 plus 1 over S. Right? Let me call this current over here I prime, which is current through both 1 over S and 2. What is I prime? It is a current divider. Do you agree I can compute it? So what is I prime? Does anybody want to tell me what it is?
S.
If it's a current divider, it's proportional to the value of the other branch. So it is S over S plus 2 plus 1 over S times the value of the source, which is I. Right? Let's simplify it a little bit. I got S over S squared plus 2S plus 1 over S. So I'm just going to bring it to the top. Remember, this one down here is S plus 1 squared times I, which is this guy over here. So it is S squared. I have 4S plus 12. Right? This and this cancel each other out. So I got 4S plus 12 divided by S plus 1 squared. But that's not what I want. What I want is this V out. What is V out? It is this 2 times I prime. Right? So it's 2 times I prime, which is 2 times of this, which is 8S plus 24 divided by S plus 1 squared. Right? Which again, we can look at the Laplace inverse, and we can get V out of t to be 8 times e to the power of minus t ut plus 16 t e to the power of minus t ut. Right? So as you can see, if I go from time domain to the S domain, I can certainly apply whatever method that I knew, AVL, KCL, voltage divider, current divider, superposition, source transformation, Thevenin, Norton, all the methods that we know. And we can solve the circuit in S domain, right? And given our solution in S domain, I can always use the partial fraction decomposition to decompose the output into things, into terms that I know what they are using the Laplace table. And I can find the inverse of those terms. Is that clear how we're doing this? What's very, very important is that if I have a capacitor or an inductor, if I go from time domain to the S domain, it is not just the value of the L or C multiplied by S or 1 over SC. It is always followed by a voltage source, and the value of the voltage source depends on the initial condition of the inductor or the capacitor. And remember, this initial condition is the one that is continuous. If it's inductor, I know current through inductor is continuous. So it depends on I through inductor at time 0. Or if it's a capacitor, I know voltage across the capacitor is continuous. Therefore, this voltage source depends on the voltage across the capacitor at time 0. As soon as I know how to go from time domain to the S domain for every single element I have, the rest is just very simple. Right? Does that make sense to everybody? We definitely have one question on this on the exam. That is the last question we have on the exam. Is that clear to everybody? Fantastic. I'll see you guys Wednesday.